Number 5? Yeah? 3C. Wow, so I literally have something. Wait, didn't you say elephant said it was right?
Good morning, everyone. Good morning. So I'm going to continue from the problem we saw last time, because I want to talk about how to draw the bending moment curve, and then we will get to a new problem after that. Okay? All right. So first things first, I'm going to quickly draw the figures from last time. You already have it with you, and I also have posted pre-lecture slides which have these figures, so you can take a look at it. So this was the beam with all the loads acting on it. And these were the distances. X is equal to 0, all these distances are in meters, okay? X is 1, X is 3 meters, right at the end of the distributed load. Then I come to the couple moment, which is acting at X is equal to 6. And X is equal to 8 is the end of the beam. Okay? All of these are in meters. We were able to draw the shear force diagram for this particular setup as the following. So what I want to do in the next problem is, at least with the shear force diagram, when we draw the shear force diagram, I don't want to perform calculations. I want to see the load distribution that is acting on the beam and then directly start drawing it out. So here is how I look at it. This is how I do these things. 175 newtons, concentrated force pointing up. Start there from 0. That was 175 newtons. Then between x is equal to 0 and 1, there are no forces acting, which means that if I start at 175, it's going to remain at 175. Okay, so I go constant, okay, 0 slope, because there is no force acting there, no distributed load acting there. Then I know that at 100 newtons per meter, I have to subtract from the 175. Okay, so there's going to be 175 minus the area under the distributed loading. It's negative is because this is pointing vertically down. So there's going to be 100 times 2, 175. So I have to go to minus 25 at x is equal to 3 meters. Okay, so this was at x is equal to 3 meters. So how do I go from 175 to minus 25? The slope of the shear force diagram is equal to the load intensity. The load intensity here is constant and negative, which means that the slope of the shear force diagram is going to be constant and negative. So I'm going to have a linear or a straight line motion from 175 newtons all the way to 25 negative. Okay, so this is in the following manner. And then we obtain this point of 0 crossing using the similar triangle idea. So 0.25 meters. And this was at x is equal to 3, 1, 0. Then all the way from 3 all to 8 meters, I see that I don't have any distributed loading. And eventually I just have to keep following a 0 slope pattern from 3 meters to 8 meters. Along the way I cross this 6 meter mark. And then at the end of 8 meters I see that I have a force of 25 newtons acting vertically up. So this is going to push me from minus 25 all the way to 0. Okay, so this is my shear force time. Were there any questions on the shear force time? Yes.
So if that wasn't a distributed loading and it was just like a single force, would it just be a direct line downwards instead of a slant?
Absolutely, absolutely. It will just have a singularity, and that's what we're going to see in the bending moment curve. Okay? All right. So when you're drawing the bending moment diagram, you need. Okay, your question.
So although we've taken a look at linear and quadratic lines, are we also going to look at cubic?
It can be anything, right? If the slope is a linear slope, the curve is going to be a quadratic. If the slope is a constant, the curve is going to be a linear. If the slope is a quadratic, the curve is going to be a cubic. So the curve is always going to be 1 degree higher than the slope. That's exactly what I'm going to be talking about when I do the bending moment curve. Okay. All right. So you need this. You need this. I'm not going to do the bending moment calculations. We already completed that. I just want to see how to draw that curve. Okay. M in Newton meters. Okay, so I have my marks here. So 0, I start at 0, and then I have 1 meter. Then I have this point of 0 crossing. Always remember, if the shear force is crossing the x-axis, the point of crossing is either a maxima or a minima for the bending moment time. Okay, so there is some special event taking place there. So that's going to be 2.75 all the way from x is equal to 0. So I'm going to mark that on my plot here. Then I'm going to have the end of that 3 meters. x is equal to 3 meters. Then I'm going to go and say that, okay, I'm going to mark this x is equal to 6 meters because there is a couple moment acting there, so that's something special for me there as well. 6 meters. And then 8 meters. Okay, so these are the points that I typically mark on the bending moment diagram. I start off by saying, okay, I'm sitting at 0. We obtained m at x is equal to 1 as 175 Newton meters, which was a positive value. To go from 0 to 1. I need to look at the slope of the bending moment. Okay, so dm by dx is equal to the value of the shear force. Look at this carefully. Go to the shear force diagram. Between 0 meters and 1 meter, the shear force is positive and constant. It's positive and constant, which means that the bending moment curve is going to be linear with a positive slope. Okay? And I'm going to go from 0 to 175 meters, a Newton meter, in a linear fashion. Okay? Does this make sense to everybody? You look at each and every piece of the shear force diagram to figure out how to draw the bending moment curve. Then I go from 175, I go from x is equal to 1 to x is equal to 2.75. We had calculated that value last time, it was 328.125 Newton meters. To go from 1 meter to 2.75 meters. Slope of the bending moment diagram. Look at this. To go from 1 to 2.75, that is x is equal to 1 to x is equal to 2.75, the slope of the bending moment diagram is equal to the shear force value, which is positive and decreasing linearly. Okay, so this is V of x, positive. Does this make sense to everybody? So if the slope is decreasing linearly, the curve, which is going to be the integral of the slope in some sense, is going to be a quadratic whose slope is going to start off as the slope at this point. And when I reach x is equal to 2.75 meters, what is going to be the slope of the bending moment diagram?
0.
It has to be equal to 0 because that is the value of the shear force at x is equal to 2.75 meters. Okay? So I have to go to 0 slope starting from here. So look at this. This is going to be a quadratic. Why is it a quadratic? Because dm by dx is linear change. The curve is going to be a quadratic. So the curve 1 degree higher than the slope. Which means if the slope is linear, the curve is quadratic. If the slope is a quadratic, the curve becomes a cubic. It is going to be the case in the next problem that if you have a triangular distributed load, the slope of the shear force diagram is equal to the load intensity value. So the slope of the shear force diagram is going to change linearly. The shear force is going to be a quadratic. The bending moment slope is going to be a quadratic because the shear is changing quadratically. So the bending moment curve is going to end up being cubic in our next problem. Okay? And likewise, okay, I can just keep writing this until eternity and so on. Does this make sense to everybody? Slope, what is slope? The slope here is the same, it has to be continuous, the bending moment curves are continuous except when you have a concentrated couple moment. That's where you see a discontinuity. Okay? I reach at x is equal to 2.75 meters, my slope becomes 0, so if I draw a horizontal line, that tells me that the slope is C. Okay? Question? Any questions? Okay, so we'll move on then. So I have to go from 2.75 meters, I got to go there to 3 meters. So I write it out again. From 2.75, and I need to see these things in your work as well. You've got to tell me why you're drawing certain things the way you're drawing them. This will be a quadratic for me. I need you to label the curves as well. Okay? From 2.75 to 3 meters, the shear force value, watch out, is negative and decreasing linearly. Negative and increasing linearly. Okay, so dm by dx is negative and its magnitude is increasing. Look at this, I'm not saying that the shear force value is increasing. The magnitude of the shear force value is increasing from 0 to 25 newtons. From 0 to 25 newtons, the magnitude is increasing. What's the sign of the shear force? It's negative. So when I write it as negative and increasing, I mean the magnitude is increasing. Which tells me that the bending moment curve is going to have a quadratic shape with slope given by that. The slope is negative and increasing. Okay, so I am falling down essentially. Starts at the same slope as I left off in the previous piece. It's a small drop that I typically see. This is 325 Newton meters. So this was 328.125, and then here 325. Does this make sense to everybody? I start off with a 0 slope. The magnitude of the slope is increasing as I come to the end of x is equal to 3 meters. But the slope is negative, which tells me that the value of my bending moment is falling down. Questions? Yes?
On this shear force diagram, so for 3, why is it so, I know it's negative because it's like below the x-axis, why is it increasing? If
Right.
it's going
Right. So when I say it is increasing, so we have discovered that it's negative. Right. So set that aside. It is increasing because I am looking at the magnitude of the shear force, which was 0 here, and then becomes 25 newtons. Just the magnitude. Okay. So this is just the magnitude I'm looking at. And when I said likewise here, I was looking only at the magnitude of the shear force. Okay? So account for the sign of the shear force, which is going to tell you whether the slope is falling down or climbing up. And then account for the magnitude of the shear force, which will tell you how is the slope changing. Is it positive and decreasing or increasing, or is it negative and decreasing or increasing? Yes, sir.
Is it also okay if we were to take a cut of the beam and determine the moment caused by the distributed force and find the quadratic from
You could do that, it's kind of laborious, right? Because if you have a large number of loads acting on the beam, then it's going to take a long time.
So we'll never actually have to find the quadratic for, we can just graph it what it should look like.
Absolutely, absolutely. Yeah, that is the beauty of this thing is that, you know, you can actually cut the beam at several locations, find out an expression in terms of x, like what we did the first time we looked at the shear force impending moment diagram, but that's kind of laborious.
Okay.
Here I would have to make a cut here, a cut there, a cut there, and a cut there. Right, so that's why this is a much more powerful method.
Okay.
Yes, sir.
Just have a slight form of confusion. Before we drew the quadratic curve, we went ahead and drew the straight line. We can.
No, the straight line says that the slope is 0.
It says that the slope is 0.
At this point.
Yeah. Do we go ahead and pick that up from that straight line or from the previous quadratic curve?
So it is, this curve ends here. For this piece, it starts here. So you see, the slope here is the same as the previous. So the slope at this point, there is no discontinuity. So it picks up here. This piece, starting from here all the way to there, is a quadratic. That tells you the evolution of the bending moment from x is equal to 1 meter to 2.75. Then I got to go from 2.75 to 3. So I start off with the same slope value. And then I fall down a little bit because I'm told that the slope is negative. But the magnitude of the slope, so look at this. How do I draw the slope? If I have a curve, some random curve here. What's the slope at any point? The slope at any point is the tangent at the point, right? So I just draw a tangent here. That's the slope at that particular point. I draw a tangent at some other point. That's the value of the slope at that particular point. So if I have a curve of this nature, I see that there is going to be a point of inflection where the slope is going to start changing signs. Okay? So we will come across those things as well in our bending moment curve, but for the time being, if we just focus on one particular piece, for example here, if I have a curve of this kind, is the slope increasing or decreasing? Okay, so I have a curve of this nature. Okay, this is bending moment. This is x. Is the slope increasing or decreasing? There is no need to guess. We can draw it out. All I need to do is draw tangents at each and every point. There's one point here, there's one point there. I start off as a horizontal line. Horizontal line means zero slope. Then I slowly start increasing and become almost vertical. So this is an increasing slope. Okay, so here the slope is positive because I'm starting from a small value and going to a larger value and increasing. I can draw many different types of curves. I can take a curve and draw a slope that is decreasing and negative. Okay, does this make sense to everybody? And maybe what I'll do is I will write out these things on a notability file and then I'll upload it so that you also have this when you're doing your problems. Yes, question?
Is the equation of the quadratic the same on the left and the right side of 2.75?
Not really. Because one equation, if I take the derivative, it's going to give me a positive slope. The other thing, if I take the derivative, is going to give me a negative slope. And the value of the slope is also changing in a different manner. Okay, so they're not the same equation. They're quadratics, but not the same.
Why couldn't it just be like, I don't know what it is, call it negative x squared, you know, how it kind of goes like that?
So if this was positive x squared, and then you're saying this is negative x squared.
Well, it's a negative hyperbola, right? That's what it's called.
Negative parabola. Parabola.
Yeah, so that's why I'm like on both sides, and then that's just the max.
Alright, so what I'm trying to say is if I take the magnitude of the slope at this point, and I take the magnitude of the slope at this point, they are not necessarily the same for both the curves.
Right.
Which is why their equations are not going to be the same. They will be of the same form, they will be a quadratic. One is an increasing slope, the other is a decreasing slope. Okay, and if there is doubt, one can actually slice it at some point before 2.75 meters, slice it after 2.75 meters, find out the equation in terms of x, and see it. Okay. So perhaps you can do these things in your homework assignment. I'll try to make you think along these lines and see if these pieces are the same equation or not. Okay. So we will continue with our discussion here. I stop here at x is equal to 3 meters. Then from 3 meters to 6 meters, I'm falling down to around 250 Newton meters, somewhere here. Okay, so this is at 6 meters. I have to actually go in the same, I have to have the same slope, so I'm just going to change my I'm going to call that as 6 meters, okay, because I have to have the same slope when I drop off here. And as I go from x is equal to 3 to x is equal to 6 meters, as I go from 3 to 6, the shear force is negative and constant, which means that the slope of the bending moment is negative, so it is falling down. And it's a constant slope, which means it's a linear curve. Okay. Then at x is equal to 6 meters, I see that there is a couple moment of magnitude 200 Newton meters, which is counterclockwise, and you obtain the value at that point as 50 Newton meters, so you will see a sudden sharp drop. You'll come all the way to 50. That's the discontinuity in this bending moment curve. And then I go back home in the same manner as I started from 6 to 8. I see that the slope of the shear force diagram is negative and constant, which means the value of the shear force is negative and constant. So I drop off in this particular manner. Okay, so this is from 6 to 8. This is 3, 2.75, 1 not drawn to scale because of the fact that I want to have continuity at each point. There is no continuity here. This is discontinuous. The slope of this portion is the same as the slope of that portion. They are parallel lines essentially. Why is that? It's because the shear force value does not change its magnitude as I go from 6 meters to 8 meters, or as I go from 3 meters to 6 meters. Okay, this is still minus 25, so the slopes are the same for both these lines. These are parallel lines. Same slope. This portion here is a quadratic. And this is your bending moment. Once again, there is no substitute for practice. Okay, if you try solving different types of problems of different varieties, one will be able to look at these curves and then draw them directly, okay, without extensive calculations. I want to see if there are any questions on this problem. Yes, sir. Question.
So for the bending moment diagrams, will the counterclockwise couple moments always be negative?
Yes, that's what we derived a couple of lectures back, and that's something that I pointedly suggested, that it is against our common intuition that if I have a clockwise couple moment, it causes a positive jump in the bending moment. If I have a counterclockwise couple moment, it causes a negative jump in the bending moment diagram. And we also calculated the value here last time, and we found that it was dropping from 250 Newton meters to 50 Newton meters. Yes, so straight down. So that's a singularity that is happening here. Whenever you have a concentrated load, singularity in the shear force diagram, you see a singularity spiking up. I have a 25 Newton meters spiking up or down. Okay, in this case, if I have a couple moment in the bending moment diagram, I'm going to see a spike or a discontinuity or a singular event taking place. Question?
I'm struggling to understand in part C where, so the slope of the shear force diagram is negative and it's increasing. But I'm starting to see the increasing part on the bending moment diagram. Where did you, how do you draw that again?
Okay, so I guess let me do the following. let's construct all of these things. Okay? Positive values above, negative values below. Let me consider a curve. Tell me what the slope of this curve is doing. Increasing or decreasing?
Increasing. Increasing negative.
Decreasing and
No, increasing negative.
increasing and negative. Why is it increasing? Is because don't guess any of these things, please. There is no guessing here at all in physics. Okay, it is actually changing signs. That's the first thing. Okay, but let's forget that. Let's say that this is starting off as a zero slope. So if I draw it out this way, at each and every point, I just draw a horizontal line or a tangent line. Sorry, here it is horizontal. This is horizontal at this point. So I start at zero slope. At some other point, I draw the slope. Draw the slope. What is the slope doing? The slope is increasing. And what about the value of this? Let's say this is the bending moment. The value is starting off at a high value and going down, which means that the slope is negative and increasing. Okay, so this is negative. Does this make sense to everybody? Slope is negative, so the value of the bending moment or whatever quantity that you're considering there, the value of that curve is reducing from where it was initially to where it is now. Doesn't necessarily make the value of m negative, it is just decreasing in magnitude, but the slope is increasing. Start off as a horizontal line of zero slope, keep increasing. Okay, let me draw another curve. So I'm drawing this in the negative portion of the graph that I'm showing here. Can anybody comment on the slope of this curve?
Decreasing.
And to help us out, I'm going to draw tangent lines. That's the tangent line at that particular point. That's the tangent line at that particular point. That's the tangent line at that particular point. What's the slope doing? The slope is
Decreasing.
decreasing, and is it positive or negative?
Positive.
Positive because it's taking something that was negative and making it less negative. Okay? So this is now an increasing, a decreasing, and negative, positive, I'm sorry. Does this make sense to everybody? Do you want one more example? Let me maybe do one more example. Okay. This is M. This is X. You guys have a question? Question? Okay. M and X. I'm drawing it in the positive quadrant. Once again, I'll start drawing slope lines. There is no guesswork here in any of these things. This is the slope at that point. This is the slope at that point. Choose another point. That's the slope. Assume this to be almost horizontal. Okay, so can somebody tell me what the slope is, what the nature of the slope is? Yes, sir.
Decreasing, negative.
Decreasing and negative. Fantastic. Okay, yes, sir.
So you could almost, correct me if I'm wrong, you could always just look at the concave edge of the curve.
because concavity and convexity depends on perspective. If I'm sitting on one side of the curve versus the other side of the curve, what do I call it, concave or convex? It can depend on the perspective of the viewer. So I would never want to use concavity to define the characteristics of a curve. A curve is characterized by its tangent. The tangent is nothing but the tangent line at each and every point on the curve. You draw the tangent line, you look at the inclination of this tangent line, it was initially at a certain angle, right? So what was that angle? Let's call that as theta 1, that's the angle there. Then here, theta 2, you see that theta 2 is lesser than theta 1. Then I essentially come here and if I draw theta, theta is 0. Okay, and then it is negative because I'm pointing down. If the slope is pointing down, it's negative. Okay, and the magnitude is the magnitude of the slope of the angular, the tangent angle, that is theta. Okay, that's the magnitude. All right, I'm going to move on to the next problem. I'm going to get a head start on that. Next problem is an interesting one. It's a cantilevered beam. You have the figure given to you. You have the support reactions calculated as well, so I'm going to skip all those parts. The problem. It's a cantilevered beam. I'm not going to show the fixed support. Instead of showing the fixed support, I'm going to show the effect of the fixed support. Okay? So that's going to give me a reaction force A suffix y. I'm going to have a reaction moment. MRA is the reaction moment because it's a cantilevered beam. I have the following forces acting on this beam. Newtons per meter, triangular distributed load acting over a span of 6 meters. Then I have a concentrated force of magnitude 300 newtons acting at 3 meters from the start of the beam. Once again, I'm not showing the fixed support. There was a fixed support here. I'm showing the effect of the fixed support. Okay? In the file that I posted on your Carbon page, I'm showing the fixed support. I'm calculating the support reactions. After free body diagrams, static equilibrium and everything, you'll be able to obtain AY as 900 newtons. And MRA is a reaction moment, which is a couple moment at the fixed end, which is going to be equal to 6,900 Newton meters. This is after performing the statics part of the problem. Okay, all of this has been posted on your Carbon page if you look at the pre-lecture slides. What I want to do is I want to draw the shear force diagram and bending moment diagram without performing any calculations. Okay, so let's do that. Okay. Let's start off by drawing the shear force. Okay. Help me out. How do I start at x is equal to 0? What do you see on the free body diagram? At x is equal to 0, so if you want, this is x is equal to 0, x is equal to 3, 6, x is equal to 12. At x is equal to 0, what do you see? You see that there is a force that is pushing you up, so you go up.